I'm from the University of Tokyo, and today I want to present to you about a method to evaluate the concrete-based materials for 3D printing. So I believe most of you, we've never met before, so I firstly want to introduce ourselves and introduce our project. So our project starts from Spain, and it's when our team leader Yuta he was fascinated by the architecture of Gaudi and this Guo Park and Sagrada Familia, and these organic shapes of the architecture makes you feel as if those architects are alive and the stones are growing and moving. That motivates you to want to go there again or make that kind of architects. So we think about how to make these kind of architecture by ourselves. And so in order to make these kind of unique or organic architects, we believe that especially the three-dimensional shape is important. The three-dimensional walls is difficult to make, and we think that's the key difficulties that we have to conquer. So what we are doing right now is, maybe most of you know, that we make formworks and put inside concrete and wait for it to be molded. And if we want to make three-dimensional walls by that, we need to make the formworks all by our hands or using huge machines to make these kind of things. And it's really costs a lot. And we think that is quite a hard work. And so what we have done is very quite simple. We think that 3D printer can lead to less limitation of creating walls. And well, this is our vision of what kind of things we want to build in the future. I believe yesterday, there are lots of talks of new forms of architects, and we want to show you a little more example of what kind of application of 3D printer in architecture field right now is working on. And we think that mostly there are two different types of 3D printer in architectural field. First is about robot arms. We use KUKA or huge other different robot arms, and to make these kind of curved walls. And another type is first making is delta type, having a huge construction before making the 3D printer, the third one. So we have to make a construction before making construction, and we think that is kind of problematic. And also, the problem of robot arm is that robot arm itself is quite expensive, and when we want to move that to other places, it's quite big, and you need the rails to move, or you need rail beforehand, to build the rail beforehand. So we think that we have to use a quite new method, a new style of 3D printer, and that's something we want to present to you in the first place. And this is a small preparation. Well, there is no sound. So this is the kind of new concept that we want to present, that we want to make So we want to make a large building with a very small 3D printer, which means that we want to make it like a robot form, and when we want to use this robot to print out materials and use that materials as a rail of it himself, so that he can move on its rails and move on climbing the wall, and so that it can put out less limitations of the size or less limitations of the construction time. So you just bring the small 3D printer on the side, and you can make the new type of construction. And that's the kind of new concept we want to bring into the architectural field. And so we call this robot Archileon, because we think that it's just like, well, we inspired from Gaudi, so chameleon is a kind of concept we want to introduce. And well, this project is quite not like finished yet, so it's really a little bit small construction prototype. And this is a progress we are moving on. But this is a difficult, today we want to present the paper we talk about is a little bit different topic. So when we want to make these kind of new 3D printer or just architectural 3D printer, a large difficult problem we have to face is to choose materials. Like when we want to make those kind of three-dimensional walls, the materials that have high viscosity is needed. But when we want to print out that, we have to transport it, and after transporting it, we have to make the materials stay on the top of the last layers, which means that we have to consider these two types of requirements. And today we make it is relatively lead to high viscosity, but we can make it a new term, which we call it formability and fluidity. And which means that formability, as you can say, is if you don't have a good formability, the upper layer will lose out on the last layer. And if you cannot fluid enough to transport through the pipe, you will just clog on that pipe, as you can see. And why we focus on this problem is because that we have faced these kind of bad materials a lot of time, and because the concrete material is a very large group of family of lots of ingredients, and we have to design the ratio all the time. And that's the problem that's the reason why we face it. And we think that right now we need evaluation of these kinds of materials to test the property we showed before. But what we can do right now is, firstly, we can, of course, just visually evaluate that and by printing out it directly, or use the lab instruments like this Cometer. And there are two different kind of evaluation. Yeah, the first one is quite simple. You just print it out and just see it, but it cannot be tested quantitatively. On the other hand, the lab instrument is very very precise, but it still cannot be doing a lot of time because it's quite expensive. And also, another timing when evaluation is necessary is you have to make it on the site of construction. So like slump corners test, they have to make it every time before the construction because they have to maintain the uniformity of the materials, which means that a very simple evaluation is necessary. So today we want to introduce a new method that is simple but also quantitative. So now I want to talk about what kind of method we will try to use. So today, there are two properties we want to test. First is about the formability. And that we use a flow tester that we want to show you is to test the formability. In the first place, we try to use the traditional method, slump corns, to test the materials that we want to use. But as you can see, just cannot make it form. The reason why we think that is because it's too sticky and stick to the walls of the slump corns and make it difficult difficult to pull up. So therefore, we just change a little bit of the former type of traditional method. So we just make it straight and make it take off the top of it. So make it the air getting to more smoothly, and by making it straight, make it more easy to come out. And the different point is that by making it straight, we have a better model of formability, which means that when you test it on the straight form, you can know the upper layer and last layer, what kind of change of upper layer and the last layer. So it's better modeling the real situation. And about the fluidity, well, fluidity is about whether material can be transported, and specifically is about whether material can reach the pump with its own gravity. Why is that? It's because when we try to use the motors, when you put inside the materials have to get inside the pump in the first place without using any force other than its own gravity. And this is the kind of problem we face, and therefore we try to use another method to evaluate that. So this is also simple, like we try to use the same model. We model the liquid port of pump, and we call it Flux tester. And we put inside the materials and wait for it to come down and test and measure the flux level, that how long that it comes down by its own gravity. And finally, we test whether our evaluation method is usable by using these known materials. We used 4 different kinds of samples to choose which material to have. We use 4 samples that has good fluidity or bad formability. That sample 4 is quite a good one, but other thing that has something has poor fluidity or something has poor formability. And then we use the proposed method to try to test whether it is good or not. And as you can see, the result is on the right-hand side. The x-axis means that the fluidity is high, and the y-axis means formability. So the colored corner means that it's more suitable for 3D printer. And as you can see, this number 4 is on the right area, which means that it might be appropriate to use in 3D printer. And actually, we tested with the 3D printing robot we have, and actually shows that it can be make constructions onto the layer. So it's kind of very. So actually, we have done a lot of more deeper conclusions of what kind of materials, what kind of ingredients can lead to a better formability, or what kind of ingredients can lead to a better fluidity. For example, like fly ash can lead to good formabilities or not. And we think that this time we just only use 4 different types of ingredients, 4 different types of samples. And by increasing this type of samples, we can show a lot more than this, and test with different materials can also lead to a better results. So finally, the thing we want to say is that first, for materials of architectural 3D printer, there are 2 key properties that we have to notice. Maybe right now there are other different kind of properties, but we believe that by using a much more easy to know method, they can let more people who are new to it can use the same kind of properties and make it more different type of samples. And using these kind of simple and quantitative evaluation method can lead to more contribution to 3D printing in architecture. Thank you.